Hello everyone, this is Kelvin. So today I like to talk about Newton-Leibniz law of integration. So this formula is an important fundamental theorem of calculus, and students often employ this formula to compute the definite integral of a function f of x, or we could say the area under the curve f of x. Single variable calculus students are probably familiar with this, but how it's derived or where does it come from? So in this video I'm going to show you how to prove this theorem just by using some simple calculus techniques you already know. So here we go. First, I draw a function with a curve in the Cartesian plane and divide it into infinite amount of partitions. So there are two premises here. So the first is that the function f of x is integrable on the enclosed interval a and b, and two, let partition be any partition, let delta be any partitions of closed interval a comma b. So what we want to do, so the key to prove this theorem is to start with the key to prove this theorem is to start with so the proof, I'm going to write it here. So we start with f b minus first. So we have these 2 points. So this point would be f of b, and this point here would be a f of a bracket. So the key to prove this theorem is to start with f of b minus f of a. So what we want to do here is to prove that the integral from a to b f of x is equal to f of b minus f of a. So here we go. So first we want to start with f of b. So first we want to start with f of b minus f of a. And by pairwise subtractions we can, so this would be equal to x naught f of x n minus f of x n minus 1 plus f of x n minus 1. Okay, so these two will cancel each other out. So does the like terms later. So I write this to notify that, to notate that the like terms cancel each other out, and we have plus fx naught fx 1 minus f and we have minus So we can write it like this, and this would be equal to the infinite series, and adding series where I is equal to 1 and adding all the way to n, and bracket f x I minus f x I minus 1 bracket. Right? You can try it yourself. This would definitely work. So we have to write it in this form, and then since this function f of x is integrable on the closed interval a to b, therefore in each subinterval the function is still continuous and integrable. Therefore we can apply MVT, which is mid-value theorem, in each interval you're in on this curve. So apply MVT. Then we would have, so this states that on this interval there must be a value of c on each subinterval. So MVT states that on each subinterval there must be at least one value of c where at least one value of c where the derivative, which is the tangent at c point, would be equal to the secant line of the interval. Divided by xi minus xi minus 1. And we know that f prime of c is just f is just f c if this is just this, and xi minus 1 is just delta x. This is c. So if we multiply both sides by delta x, we have f sub c, and is equal to f of x I minus f of x I minus 1. So if we take both sides, the infinite limits, so we have and I is equal to start from 1 ci delta x is just equal to antiderivative. So this would just be equal to f of b minus f of a. And this here is just the area under the curve by just the area under the curve. So this sign here